In section 3, we're going to get back into some nitty-gritty, so we're going to go back away from our graphing. Going to kind of go back to that stuff that we had done in section 1, where we did just strictly equations. But the biggest thing that you still need to know is that logarithms and exponentials are inverses of each other. And because they're inverses of each other, it also means that the properties or the laws of exponentials are pretty much directly related to the laws of logarithms. So we have 3 that probably make the absolute most sense, and then another one that is nice to do because it's going to help us do a few other things. So the product law of logarithms. So a logarithm is of a product of numbers can be expressed as a sum of logarithms. So what that means is if we have the logarithm of 2 things being multiplied together, it's actually just adding their individual logs. So where that goes back to our exponentials is if we had something like x to the power of 3 times x to the power of 2, well, that was just adding those exponents. So we have the same base, so the same thing, we're just multiplying, we're just going to add the logarithms, add the exponents. So yes, it would be x to the power of 5. The quotient law, well, if we have 2 things and we're dividing them, we're just going to subtract the individual logs. So again, if we had something like x to the power of 7 divided by x cubed, well, we did that by taking 7 and subtracting 3. It was x to the power of 4. So it's directly related. That division is a subtraction of individual logs. Power law is if we have some kind of some logarithm and it has an exponent with it, what we're doing is we're going to multiply it out in front. Now obviously I'm going to show you all of these things again, but where that comes into effect is if we had something like x to the power of 4 to the power of 5. Well, what do you do to those exponents? You multiply them together. So it becomes 4 times 5, which is 20. With the logarithm, it's literally just going to be multiplied in front. So again, we're going to have lots of examples of it. Now, the last one is a little bit of a fun one that is actually really useful to do. It's not strictly in the Pre-Calc 30 curriculum, but it fits so beautifully, and you'll do a little bit in calculus. I can't remember whether you do it quite this extent, but I know at university I've used this property a huge amount of times in university calculus courses. Basically, in order to find any kind of logarithm, so log base c of x, you just take the log of x and divide it by the log of c. Where that ties into what we've done before is, I think the exact question in our notes was like log base 2 of 14, where we had to do a little bit of estimation and like our guess and check to see what would it be. But what that really means is if we take the log of 14 and literally just type in to our calculator divided by the log of 2, it equals 3.807354922. So if you were to estimate as 3.81, that's as close to 14 as you're going to get. So this is just kind of, again, a little bit of an extra bit, but it comes in handy so well. We're going to use these first 3 a lot, try and do as many equations as we possibly can. So again, multiplying 2 things, we're adding the individual logs. And it goes both ways. We're adding individual logs, well, it's just multiplying the 2 big things. Quotients, well, dividing is subtracting. Again, it goes back and forth. I think I should really just change these symbols to I mean, it does say equals, which it does say, but just to say that they go back and forth. So if you have that multiplication in front, it actually is an exponent too. So let's use it. We're going to write this one as individual logarithms of x, y, and z. We want to write everything as we basically just want to have things that only have x, only have y, only have z, and we're going to make them as individual as possible. All right, first things first. Log base 5 of x times y divided by z. Well, we have a multiplication here and we have a division here. So really quickly, it'd be the log base 5 of x plus log base 5 of y. So what this is saying is that it's actually the x times the y. We're going to go back to this property here. Two things multiplied together, well, we're adding their individual logs. But because that entire thing is being divided by, so that x times y is being divided by z, we would be subtracting a log base 5 of z. These are individual logs now. That's it. Now, you don't necessarily need to have those brackets, but I know in some things, actually we'll see it right here, that's going to be very useful to have some kind of brackets like that. Alrighty, in this one, so we have log base 7 of the cube root of x. Well, this isn't the only way that we can write the cube root of x. We can also write it as x to the power of 1/3. What happens with that 1/3? Well, if we have something with an exponent, it just gets multiplied out in front. So we'd have a 1/3 log base 7 of x. So that 1/3 just goes in front. Now we have it completely individual. We just have that x. This next one's going to be a little bit tricky, but that's just because I'm going to show you a few things. There's two ways of treating this. The first one is actually the long way, and I'll show you it. The log base 7 or log base 6 of 1 over x squared. So that's going to be the log base 6 of 1 divided by, so division means subtraction, log base 6 of x squared. Okay, so that works. Well, what we need to know is that log base 6 of 1, so I'm just going to bring that kind of a side note up here. Log base 6 of 1 equals x. So in order to solve it, 6 to the power of x, whiplash, equals 1. What is this? Well, it's 0. X is 0, which means this entire part just is 0. And you don't actually have to write 0. The only extra bit is that exponent, that 2, has to be multiplied out in front. So we'd have a -2 log base 6 of x. The shorter way of treating this is realizing that because we have that only an x squared in our denominator, it can become a negative exponent in our numerator. Of course, I'll explain what I mean. 1 over x squared is the same as x to the power of -2. So that exponent gets multiplied in front. We have -2 log base 6 of x. And there's that. That's all there is to it. Both the exact same answer. This one was a little bit more work. All right, now time for a fun one. And yes, I do actually mean this in a very serious matter. I'm going to save a little bit of work with my work because square root of z does mean z to the power of 1/2. Remember into notch, which is 2. Exponent is 1, 1/2. All right. So write them individually. Log. What would our normal base be? What is our regular base for log? Hopefully in your head you're saying 10. So log of x cubed being divided by. Now it's being divided by this entire denominator here. Again, keep in mind that that's just exactly what that square root of z is z to the power of 1/2. So it is exactly what's in there. But because you're dividing by both of these things, you are going to subtract the entire or each of these individual things. So log of y, but in that denominator, we're multiplying. So as long as we have that bracket, we're multiplying these two, but it's being divided. This x cubed is being divided by this y and z to the power of 1/2. And now we just finish it off. Those exponents have to get multiplied in front. Now it's only going to be multiplied in front of each individual log. So 3 log of x, subtracting, I can leave that bracket, log y plus 1/2 log z. That 1/2 is only being placed in front of that log z because that's the only one that is being raised to the power of 1/2. If it was a square root of y and z, you could actually put that 1/2 in front there. Now, this answer is perfectly fine. If by chance, and I think that you have a question very similar to it in your textbook assignment, it's basically, has that negative distributed in? I'm fine with you leaving something like this, but you'll probably see something like this and have to go backwards. Which means distribute that negative in, and it's going to look like this. I'm fine with both because they are individual. Yeah, I really don't care which one. They both work nicely. Next one, we're going to combine some things. So we're going to do some combining, evaluating, and just generally having some fun. First things first, you need to see that they are all the same log base. These ones are all log base 6, which is going to make our lives easier. So because there's the addition here, it means that this 8 and this 9 are going to have to be multiplied together. So 8 times 9. But we're subtracting this log base 6 of 2. Subtraction means division. The log base 6 just goes out in front. So 8 times 9 is 72. Divided by 2 is 36. So log base 6 of 36. This would be completely simplified, but we need to then evaluate. So we say it equals x. So 6 to the power of x equals 36. Hopefully you know that 36 is, oh, sorry, I already gave you the answer right there. 6 to the power of x is 6 squared. So that means that x is 2. We're going to apply the exact same thing, very similarly here. I know I've done this one a whole bunch of different ways. And I might as well show the few different ways. Actually, I think of mainly two. One's short, one's long. Let's see. A short way would probably be seeing that, okay, this is a 7 to the power of 1, and this is actually a 7 to the power of 1/2. Well, what happens when you have same base and you're multiplying? You add the exponents. 1 add 1/2 is 1/2. So then the question is, 7 to the power of x equals 7 to the power of 1/2. X equals 1/2. Very similarly, we could split this apart. Because it's a multiplication here, this could be rewritten as log base 7 of 7 plus log base 7 of 7 to the power of 1/2. Go down further, log base 7 of 7 plus 1/2 log base 7 of 7. Well, the good news is log base 7 of 7 are both right there. So what is log base 7 of 7? So 7 to the power of what gives you 7? 7 to the power of 1. So it means that this entire thing is 1. And we are adding 1/2 times 1, which means our answer is 1/2. It doesn't matter to me how you solve it because math is math. As long as you're showing your work and your work is right, whether you take 2 plus 4 or 4 plus 2, it's really the same thing. All right. Let's take a shot at a harder one. So first off, we have this 2 log base 2 of 12. We have a log base 2 of 6 and a 1/3 log base 2 of 27. So there's a lot of things in this one. So let's take it one step at a time. I'm just going to write that log base 2 right at the beginning because it's all the same, so we're good to go. That 2 in front means that that should be an exponent, but it's only going to be applied to that 12. So 12 squared. We're subtracting something. We're subtracting all of this, which means that's a division. And it's going to be a 6 plus, well, we're not adding, we're multiplying. We are multiplying this 27 to the power of 1/3. And then we go and simplify further. Log base 2, 12 squared is 144. 6 times, let's see, 27 to the power of 1/3 is 3. 6 times 3 is 18. 144 divided by 18 is 8. So log base 2 of 8. We're asking 2 to the power of what gives you 8? Well, 8 is 2 cubed. Our unknown is 3. Last but not least, we'll bring in some variables here. Oh, no, sorry, not last. Still have another page. Because we're going to talk about a little bit of restrictions, but it's nothing too bad, I promise. Okay, great expression. We're only going to do the restrictions on this one. Oh, we won't do it on this one just because it's a little more convoluted. Should we? We take a quick think. Yeah, I guess we'll have to, but we'll talk about that after. All right, so here's we can see that they are all log base 7, so that's great. We're going to write them as one single logarithm. So we have this x squared plus this x, so that means multiplying. So x squared multiplied by x. This one's a little bit trickier because we have this subtraction, which means division, and this 5/2. Well, that's just like 5/2 just being in front of all this. So it just gets tossed in to be that exponent. So that's all it is. And then we just do our exponent laws. So x squared times x is x cubed, divided by an x to the power of 5 halves. Well, 3. Then we do our exponent laws, same base. Oh, forgot the 7. Same base, dividing. We subtract the exponents. 3, get a common denominator. 3 over will be 6 over 2. So this would be log base 7 of x to the power of 1/2. We really want to have it as simplified as possible, which means we do want to have that 1/2 out. Now the tricky part is talking about the restrictions. I don't really go too crazy on it, but at the same time, it's something that you should know. And it comes down to this. Whatever this big number here, it has to be larger than 0. So restrictions, well, we have only x's here, so it just has that our x's have to be greater than 0. For this one, that's it. This one is going to take a little more work. But we do have a log base 5. So we have the 2x minus 2 subtracting this x squared plus 2x minus 3. Subtraction means division. So 2x minus 2 over x squared plus 2x minus 3. So now we're going to simplify, which means let's factor. Let's go back to our rational unit. Numerator, we can factor out of 2. X minus 1 left. In our denominator, we have it as a simple trinomial. So product of -3, sum of positive 2 will be x plus 3, x minus 1. Simplify. Those cancel off. Oh, forgot the 5 again. Log base 5 of 2 over x plus 3. Now this is all one thing. Let's see. You have to double check back of the book, back of textbook, whether this is what's recommended or whether it should be written as log base 5 of 2 subtracting log base 5 of x plus 3. So double check, see which it is. Now the other thing, so for our restrictions, we actually have 2 things in here. Because we have 2 things originally from our first thing. We have an x minus 1 and an x plus 3. Even though that x minus 1 has been canceled off, it can still affect everything else. So we have to say that our x minus 1 has to be greater than 0. At the same time, we also say that our x plus 3 has to be greater than 0. So solving for x, x has to be greater than 1, x has to be greater than -3. You're not going to have 2 restrictions on these. Only one of them matters. You only care about one of them. The answer is whichever one actually is going to be both. So if we say -3 is there, positive 1 is there, to be greater than 3, well, that's talking about from there. Sorry, I guess it'll be an open dot and everything that way. But to be greater than 1 would be there and everything there. If we chose a number less than 1 and we plug it into here, like 0, 2 times 0 is 0, subtract 2 is -2. You cannot take, so just do that as a side note, you plug 0 in, it would become log base 5 of -2. You can't do that. 5 to the power of something will never give you -2. Which means the only restriction here that matters is this one. So I will expect you to circle that one. All right. Word problems, all that kind of jazz. Let's rock and roll. So the human ear is sensitive to a very large range of sound. Of course, as louder that you. Oh, we're just talking about decibels, so we're not talking about pitch. So loudness, so obviously, some people can't hear very soft things because of inner ear damage, all that kind of idea. Overall, the intensity beta in decibels of the sound is defined by using this equation. So beta is 10 log of I over IO. So I is the intensity of the sound in watts per square meter, and IO is 10 to the power of -12 watts per meter squared. Corresponding to that, it would be the very faintest sound that can be heard by a person of normal hearing. So audiologists recommend that people should wear hearing protection if the sound level exceeds 85 decibels. The sound level of chainsaw is about 85. So anything above a chainsaw, you should be wearing some kind of ear protection. Of course, even a chainsaw, I would recommend it as well. The maximum volume setting of a portable media player with headphones is about 110 decibels. How many times as intense would that sound be? Well, the first thing first is see how many decibel difference is it? And that's what our B is. So 110 subtracting 85 is 25. That's going to equal 10 log I over IO. Divide by the 10. So we have 2.5. And all we're going to do is solve for basically how many times more intense, which is exactly what this is. This part right here is how many more times intense it is. Well, a log has base 10. So 10 to the power of 2.5 is that intensity. And 10 to the power of 2.5 is about approximately 316 times. Actually, I'm not going to write the X, I'm going to write times. Yeah, about 316 times more intense. Sounds that are at most 100,000 times as intense as a whispered are considered safe. Well, what is that? So we need to find out sound level of a whisper is about 20 decibels. So you can see that there's a huge difference in between what's considered safe, what's considered not safe, and a whisper. So the beta value really is talking about, okay, the beta is talking about what is the difference between what we're looking for and what that current level is. Well, that's going to equal 10 multiplied by the log of I over IO. Well, that's talking about how many more times as intense, which means 100,000. The beautiful thing you can know, actually there's two things. First off, to solve for x, we just add 20. So it'll be 10 multiplied by the log of 100,000 plus 20 long story short, as long as you're just dealing with log base 10, you can literally type all this into your calculator and it'll give you your answer. I'll obviously show you a separate way, but let's just type it in, see what we get. 10 multiplied by the log of 100,000. And my bracket plus 20. So a 70 is considered to be quite safe. So another way that this can be done is determining what is the log of 100,000. So we say it is an unknown value. So 10 to the power of x is 100,000 using our whiplash. Well, 100,000 is 10 to the power of 5. So I plug that back in here with x being 5. Not this x, this entire thing right here. 10 times 5 plus 20 still equals 70. So a little bit of fun. This allows you to have a little bit shot at having some fun. I'm just going to erase that. But I do ask you to have fun.